Now this next bit we have seen before already this year, but it makes sense to look at it again now that we're specifically talking about polynomials. So sketching our polynomials. We're going to draw a polynomial, y equals some polynomial. The y-intercept is always the constant number, the same as linear functions, quadratics, because of course they are all polynomials themselves. Let's use this as the example. I don't need to expand the whole thing out because I know I just multiply the constants together and that'll give me the constant number. So I've got 1 times negative 1 cubed, so that's negative 1, times 2 squared, which gives me negative 4. Plot that in. Okay, there's our y-intercepts. The x-intercepts are the roots of the polynomial, hang on, get it the right way around, are the roots of the equation, the zeros of the polynomial, whatever it is that makes it equal to 0. Nicely, this one's already factorised for me, so it makes life a bit easy. So we know that our x-intercepts will be at negative 1 from the first parentheses, positive 1 from the second parentheses, and the third one would give me negative 2. Okay, we have our x-intercepts. Now, out of the extremities, a polynomial will always behave like its leading term out of the extremities. And that's because you're substituting in such a big number. And as you substitute bigger numbers, then the smaller powers become irrelevant. I mean, think of it with a really small power. So just say it's x squared. You sub 10 in, you get 100. But 100 compared to 10, well, 100's a lot bigger. And that's only talking about 100. You get numbers bigger and bigger and bigger, and powers bigger and bigger and bigger, then the difference becomes huge. You see, you don't need to worry about the other terms. So for that reason, out of those extremities, what's happening out of plus or minus infinity, you just imagine, well, what does the leading term do? What would that do? So for this one, the leading term, we've got x times x cubed, that's x to the power of 4, times x squared, x to the power of 6. So if I was to say to you, just draw me a sketch of x to the power of 6, well, that's just one of those U-shaped curves, and we know it'll be concave up because the x to the power is, well, it's positive, x to the power of 6. So we know our one will start up there just like x to the power of 6 would, and it will finish over here just like x to the power of 6 would. Okay, now the actual roots themselves, once we've factorised it, they will behave at the x-intercept just like the power would. So if you've got an even power, we know we get U-shapes. Remember, the higher the power, flatter it'll be at the base, steeper at the sides. So in our one, we've got x plus 2 is squared. So at negative 2, it'll behave like a parabola. But if I add that to the information that I know it starts up here, then I know we're going to have some sort of U shape looking like a parabola here at negative 2. And it must go over here from where it starts. Okay. Well, the odd ones, other than power of 1, of course, because power of 1 will just look like a straight line, but they will look like our basic cubics, or power of 5, power of 7, all the odd ones that have that inflecting shape. And again, the higher the power, the flatter it'll be at the base, the steeper it'll be at the sides. So we've got x minus 1 cubed. So over here at 1, it's going to inflect like the cubic, but I know it finishes up here. Therefore, it must go through like that. Now, at negative 1, it's just to the power of 1. So it's just going to cut it like a straight line, like normal. Well, that gives me an idea now of what I can do. And there's a rough sketch. If I wanted to, now we've done a little bit of calculus, I suppose, we could work out the x values of these points precisely now. Because we could say, oh, when's the tangent horizontal? And then we could work out those if we wanted to get a more accurate picture. Now, if you can completely factorise the polynomial down to be a perfect, well, quadratic or cubic or whatever the power is, then it will look like that basic curve because all it's doing is shifting. Remember how we did the horizontal shift of functions? So that's all we're really doing. Okay, let's try this one. We've got x minus 1 to the 4, x plus 1 cubed, x plus 2 squared, x minus 2. Here is the picture. So let's go through all those ideas with this picture. The y-intercept, I'm going to have negative 1 to the power of 4, which is positive 1, times 1 cubed, so we're still at 1, times 2 squared, well that's 4, times negative 2, negative 8 is the y-intercept. The x-intercepts, or actually I might work out where it's starting and finishing first. So x to the 4 times x cubed gives me x to the 7, times x squared, I'm up to x to the 9, times x, I'm now at x to the 10. So it's an even power, it'll have a U shape. So again, I'm starting up here, finishing over there. The intercepts will be at 1, negative 1, negative 2, and positive 2. So working my way across, negative 2. So that's the x plus 2 squared. So it'll be like a parabola. So it starts up here, it'll come down to the parabola. So it's going to come down to negative 2 like a parabola. Then the next one is at negative 1, but that's x plus 1 cubed. It's going to come through like a cubic. So it now comes back down, inflects like the cubic. We get to positive 1, that's x minus 1 to the power of 4. It's got a U shape, but the power's a bit bigger. So you see how it gets a bit flatter at the base and steeper at the sides than, say, this parabola over here at negative 2. And that finally gets us over to positive 2. It's just cutting like a linear function. Now again, those exact turning points we could locate by working out where's the tangent horizontal, and that would get us those exact points. Okay, that'll do us for today. 10.